Okay everyone, in this video what we're going to be looking at is basically we've just spoken about relative distances in I guess where we are, the different distances that we use to describe our I guess how far things are away from us in terms of astronomical sense, and now what we're going to do is talk about the movement of things, because even though it feels like we are stationary, nothing in space is stationary. In fact, everything in space is moving ridiculously fast.
Are you sure? I feel like I'm just sitting right here right now.
Yes, it's amazing that we can feel like we are not moving because everything around us is, the relative speed of things around us.
If I throw this up, it lands right here.
Exactly.
That's weird.
The speed that things are moving around us is, a moving similar speeds to what we are. So we don't feel like we are moving. We are moving on an object that is so much bigger than what we are. It's the same way when you look out to the horizon. The horizon typically looks flat, because the Earth is so much bigger than what we are, that even though we're moving really fast, it's just, we can't understand the scale of it or sense the scale of it.
How fast am I moving then?
How fast are you moving?
I don't know. Tell me.
It's a really good question, because we're moving in so many different ways, right? I mean, the first I guess way that we can think about us moving is when the Earth rotates. So as the Earth rotates in space, we are obviously moving on the surface as we rotate around. But of course, that's not the speed at which you are moving. Depends upon where you are on the Earth.
That's true, right? If I was right at the equator, I'd be moving very quickly, because the equator is about 40,000 kilometers in circumference, and I have to go around once every 24 hours. Where if I was near the pole, I'd have to go a much lower distance. So I guess I wouldn't be moving.
Yeah, in the same amount of time.
Yeah, so I guess I wouldn't be moving very fast at all.
Yeah, that's exactly right. And so, depending on where you are, and you can work out the speed at which at different latitudes, the speed at which people are actually moving, or the speed at which the surface is moving in space of the Earth.
And that's just because as you move to a different latitude, the physical distance you are traveling is less,
yes.
Right? So it'd just be the cosine of the latitude could tell you the relative distance between the equator and you that you travel. Right?
Exactly.
So we could work out at our latitude, about 31 degrees south, how fast we're moving.
Yeah.
Interesting.
Which we will leave that as an exercise for you to do.
Yeah, wonderful.
And so that's the first way in which we're moving, but there's obviously more ways in which we're moving, because the Earth is orbiting the sun. So, just as Ben was describing that, you have to traverse the whole circumference of the Earth around the equator, just in a certain time period. The Earth has to traverse its orbit, of which the radius is 1 AU, and we do that in 1 year. So we are moving at a certain speed around the sun as well.
Yeah, and that's about 30 kilometers per second. So that's pretty fast. You don't notice that because we're just, moving at pretty much a constant rate. In the same way that, if we're sitting on a train or on an airplane, you don't notice the movement, you only notice the acceleration. One of the fun ways that Newton's laws work for us, we only notice the force of acceleration. There's no force associated with velocity.
That's, constant velocity.
With constant velocity, yeah.
Yeah.
Yes, nothing related to specifically how fast you're moving, only how that's changing.
Yes,
yeah.
Exactly. We're moving at a relatively constant speed or velocity around the sun. Hence, it would be different if that were not the case. Yeah. But
and the different planets move at different speeds. We'll talk next week about Kepler's laws and the speed of different orbits. But in general, the closer you are to the sun, the faster you're moving, and things trail off. So if we were on Mars, we'd be moving slower than we are around the Earth. If we were out at Neptune, we'd be moving quite a bit slower. Which probably makes sense. Gravity is weaker when you're further away. And so the velocity to maintain your orbit is less.
Yeah, and not only that too, because if you're just considering circular orbits at different radii, but also if you're considering elliptical orbits. So you'll know comets, for example, that are on highly elliptical orbits. They travel really close when they're sort of coming around the sun, and then when they're so much further away, they travel a lot slower. But yes, as Ben said, we go into that in more detail next week.
And yes, when we change our speed, you'll change the shape of your orbits. And so we'll talk next week when we talk about Kepler orbits about how we might travel to a different planet and build an orbit that goes from Earth to Mars. We both really like Keplerian orbits, so we're getting excited and ahead of ourselves now. But
you've probably heard the phrase slingshot maneuver, which is something that is used a lot in in these scenarios, which you can sort of
But let's hang on to that. We'll come back next week to Keplerian orbits. As much as we want to talk about them with you right now, they're great.
Yes, I guess so. We've just spoken about speed. Us traveling around the sun, but also the sun is also moving. So the sun is carrying us around the galaxy as well. So we are orbiting the galaxy at a very fast speed as well.
Yeah, and so we keep increasing in speed because gravity gets more and more, right? There's a lot more gravity required to keep us, a whole galaxy together than a solar system, which tends to lead to higher speeds. And so the Earth is moving around, the solar system is moving around the galaxy at something like 250 kilometers per second. And so the time scale to go an orbit around the galaxy, we are something like 8 kiloparsec away from the center of the galaxy, and it takes us about 200 million years to go around. So last time we were here in the galaxy, 1 galactic year ago, dinosaurs were on the Earth, kind of early dinosaurs. It's been a long time coming to get back here.
Yeah, and that's funny because you sort of, students often wonder how do we not just hit things all the time? How are we not colliding into things? And this is more to do with orbits and stuff, but also it's helpful to remember the relative distances to things. As we were saying in the last video, as you go up to the next level of the next thing that is the next furthest away, you start needing another unit to define how far it is away, because things are so far away. And even, when galaxies collide, stars don't interact with each other typically because they're so much further apart than what students often realize. So that's another throwback to what we were talking about relative distance last time.
Yeah, as we said last time, the nearest star is 200,000 AU away, and so it's a very empty space between the edge of our solar system and the next solar system. So even as Kate said, as galaxies collide, there are very few collisions, actual head-on collisions between stars or between planetary systems.
Yeah, and then moving on from us moving in the galaxy is also moving. We have our own little group called the local group, and we are all, just as we are gravitationally bound to the sun's gravitationally bound to everything else in the galaxy itself is gravitationally bound to other galaxies that are nearby.
Yeah, and the typical speeds for that is a few thousand kilometers per second. So we've added another zero on top of the velocity, and now we're really starting to talk about things where relativity matters, that we're getting up to a significant fraction of the speed of light, which is 300,000 kilometers per second. So we're really talking a few percent of the speed of light at this point. This is really, really significant speed.
It is, and then you probably know about, heading out further again, you probably know about the expansion of the universe and how, and we talk about this later on.
Yeah, but don't worry if you don't. We'll talk about it next week.
Yeah, but if you consider, as we look further and further away from us, things are moving away from us faster and faster. And it gets to a point where things are moving away from us faster than the light can actually reach us. It's moving away faster than the speed of light. So, there is a limit to what we can actually observe in the universe.
Yeah, and that sounds like it should violate the laws of physics, that things are moving faster than the speed of light, but it doesn't, because it's not that the things are actually moving away from us, it's that the universe is expanding along the way, and just the rate of expansion is so big that the light can't catch up. So it looks like superluminal motion, we call it superluminal motion, but that doesn't mean that things are happening faster than the speed of light. That is still a constant that we, as far as we know, we can't get around.
That's a good point, because it's not like space is expanding into something. But when we talk about the expansion of the universe, we'll talk about this. But space isn't expanding into empty space. It is space expanding. So, but yes, we will talk about that. But yeah, this is sort of a quick video on how fast things are actually moving, which leads us into what we'll be talking about next, which is, why the night sky is generally black.
Yeah. So since we started this video, we've moved something like 30,000 kilometers.
That's a lot.
Yeah. I guess I can skip my run tonight, huh?
Yeah.
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 Perfect.
I might too.
Yeah.
So feel free to skip yours as well. And we will see you in the next video, where we will talk about why the sky is dark.